Hi, welcome back. So today we're going to talk about section 12.3, which is antiderivatives involving, or integrals, antiderivatives involving log functions and exponential functions. So last class we talked about U substitution, and the class before that we had an introduction, well, two classes before that we had an introduction to antiderivatives. So we've talked about the power rule, where we add 1 to the power and divide by a new power, and we've talked about how to deal with slightly more complicated functions, and we use this idea of U substitution. What we haven't talked about is we haven't talked about antiderivatives for the log function and the exponential function. So we're going to talk about those, and then after we talk about those, we're going to incorporate those into our ideas of U substitutions. So let's start out by thinking about our derivatives of exponential functions. So you might remember from chapter 11 that if f of x is equal to e to the x, then our derivative, f prime of x, is also equal to e to the x. And this actually tells us something. What this tells us is if we know that the derivative is e to the x, the question is, what is the original function? And the answer is, if your derivative is e to the x, then your original function must have also been e to the x. So the integral of e to the x dx is e to the x, although I do need to add on that plus c for that constant that when we take a derivative could have gone away. So our antiderivative of e to the x is e to the x. Cool. So now you have another antiderivative rule. Now, the other derivative that we talked about is the derivative of the natural log function. So if f of x is equal to natural log of x, then our derivative is 1 over x. So the derivative of natural log of x is 1 over x. So what that means is, this tells us that if you are told that the derivative is 1 over x, then the original function must have been natural log of x. Now, there is a technicality here because the natural log function, you're not allowed to plug in 0 and you're not allowed to plug in negative numbers. So we add these absolute value bars on here as a technicality just to make sure that if you type in a negative number for x and look at natural log of that negative number, if you type that into your calculator, you don't want your calculator to explode. So we throw in these absolute value bars. And so those are there for technical reasons having to do with the domain of the natural log function. Okay, so the antiderivative of 1 over x dx is natural log of the absolute value of x. And then, of course, I want to add on that plus c at the end. Okay, so these are our two new antiderivative rules. So let's look at an example. So for our example, we have the integral of 3e to the x plus 5 over x dx. Okay. And we want to find the antiderivative of this function. So I see, first of all, that I have a plus sign in here, so I can treat each of these functions separately. Secondly, I see that I have just a plain x in the denominator, so I'm going to actually rewrite this second part of this expression. She has something to say about this. All right, okay. So we're going to rewrite the 5 over x as 5 times 1 over x. So I'm kind of pushing that 5 off to the front, and when I push the 5 off to the front, I leave a 1 as a placeholder in the numerator. Okay, so this, we can now take our antiderivative for 3e to the x. I carry along the 3, and I take the antiderivative of e to the x and the antiderivative of e to the x is e to the x. And then I have plus. Now here I have 5 times 1 over x, so I carry along the number, the 5, and the antiderivative of 1 over x is natural log of the absolute value of x. And then I have a plus c. And so this is our final answer. All right, so I do have one warning about one of these new antiderivatives. So check this out. Okay? If you're walking down the street and you see the antiderivative of x to the negative 1, okay? You might look at that and say, oh, this is x raised to a power, so I'm going to apply the antiderivative power rule, which says to add 1 to the power, so negative 1 plus 1 gives me 0, so I have x to the 0, and divide the number in front by the new power, and then of course toss on the plus c. Now here is a pretty big problem because we are dividing by 0. This is no good whatsoever. Okay? Dividing by 0 is not going to work. And here's why. Back when we learned about the power rule for antiderivatives, we said that the form for this, oh, and there was a k in the front here, we said that when you do this, you add 1 to the power, and you divide the number in front by the new power. And when we wrote this rule down, we said this rule works as long as that power is not equal to negative 1. Okay? So this is why this power rule does not work for x to the negative 1. Now, we can now actually deal with this integral of x to the negative 1 because if you look at x to the negative 1, what you want to do is you want to recognize that x to the negative 1 is the same thing as 1 over x. So if you see the integral of x to the negative 1 dx, what you want to do is you want to rewrite this as the integral of 1 over x dx, and then say, oh, I know what the antiderivative of 1 over x is. The antiderivative of 1 over x is natural log of the absolute value of x plus c. Okay? So what I've written up here at the top about adding 1 to the power and dividing by that new power, when the power is negative 1, that does not work. Okay, so let's look at one final example in part 1 of our class tonight. And if my assistant will allow me to take a look at that example, we can write it on the board. Okay, so we have, as our example, the integral of 3x squared plus 3x plus 3 plus 3x to the negative 1 plus 3x to the negative 2 dx. Okay, now this is kind of a silly example. I picked 3 because when I was thinking of this example, 3 happened to pop into my head and it was my favorite number at the moment. My true favorite number is 2,500, but I didn't want you to have to write that down every time. Okay, so the reason that we're looking at this particular example is because I want to kind of compare what happens when we have different powers of x. And you'll notice the powers on these x squared, x to the 2, x to the 1, x to the 0, to the negative 1, to the negative 2. So we're looking at a whole series of different powers here. All right, now before I go and write down any of these antiderivatives, as I'm looking at these, the one special case that I want to highlight is this 3x to the negative 1. So for that one, whenever I see an x to the negative 1, that special power of negative 1, I want to rewrite this term as 3 times 1 over x. Now the rest of them are all going to remain the same. We have 3x squared plus 3x plus 3 I've changed 3x to the negative 1 to 3 times 1 over x plus 3 times x to the negative 2. Okay, so now I'm ready to take my antiderivatives. So for this first one, I'm going to add 1 to the power. So we have x to the third. Divide the number in front by the new power. So we have 3 over 3 x to the third. For our second one, I'm going to add 1 to the power. So I have x squared. Divide the number in front by the new power. So I have 3 halves x squared. Our next term is a little bit different because it's a number sitting by itself. So its antiderivative will be to tack on an x. So we have 3x. Our next term is our special case. The antiderivative of 1 over x is natural log of x. So we have 3 times the natural log of the absolute value of x. And our last one, 3x to the negative 2, I'll add 1 to the power. So negative 2 plus 1 gives me negative 1. And I'll divide the number in front by the new power. And now I can add on a plus c. Okay, so that's an okay final answer. Maybe I'll clean up a few of the terms. 3 over 3 is 1, so we have x to the third plus 3 halves x squared plus 3x plus 3 times the natural log of x. 3 divided by negative 1 is negative 3, so I have minus 3x to the negative 1 plus c, and so this is my final answer. Okay, so in our next section, in our next part, we're going to talk about how to incorporate u substitution with our exponential and log functions.